Okay, I would like to continue with an alternative approach to dimensionality reduction, which shares some similarities with PCA, but tries to overcome one of its key limitations. And it's called Fisher's linear discriminant analysis, or sometimes just linear discriminant analysis, or just LDA, although there are different techniques which are also called LDA. So I therefore write it Fisher's LDA, or linear discriminant analysis. So the key limitation of PCA is visible if we look to data points which have a large spread in some dimensions, but those are dimensions which are not relevant for the underlying estimation problem that we want to tackle. So consider we are interested in a classification problem, and we have this dark red and this light red points. And these corresponds to points coming from two different classes, from a class 1 and a class 2. We want to do a dimensionality reduction and then perform the classification in this lower dimensional space. If we just look to the spread in the data and completely ignore the class labels, if we take those points into account, we would probably project those points on this dimension, so that it would actually look like this. And that's problematic because in this one-dimensional space, in this reduced space, it's very hard to find a separating line or plane, for example, which separates the dark red from the light red points. So if I go back to my original space, here I can say, okay, that's actually a pretty good line, which maybe not perfectly, but quite well separates the dark red from the light red points. If I do the dimensionality reduction first, it may lead to this result. And whatever classifier I apply, I'm not going to separate those points very well. So performing this dimensionality reduction has a huge negative impact on the classifier, on the classification result, because the classifier will not perform well. We, however, could think about a different dimensionality reduction. Let's say I'm not projecting to this dimension, I'm projecting along this axis. If I would do that, the points would actually be projected along these lines, and that's okay. Here I can actually do a pretty good split somewhere over here. So there is a low dimensional space, which still allows me to separate the class as well, but PCA won't find it. And this was kind of the main goal of Fisher's linear discriminant analysis. What we want to have is, we want to find a dimensionality reduction so that the classes can be separated well by a classification system later on. So my objective function is not now to minimize the reconstruction error in terms of the difference of the original data points and the data points mapped to the d-dimensional space. What I want to find is actually a dimensionality reduction so that the classes can be separated very well. But this requires that I have knowledge about which point is class, for example, 1 or class 2. So it's a supervised approach in the sense that we need to have this additional information about the data points in order to make the decision, how can we project them to a low dimensional space so that they can be separated well. So overall, we want to do a very, very similar thing. We want to find those dimensions which allow me to perform a dimensionality reduction, but the objective function is not minimizing the squared reconstruction error, but maximizing the chance of the classifier to separate those classes well. Okay? Is it clear what we want to do? Okay, great. Okay, let's go to the key idea of Fisher's LDA. So let's assume we have those data points over here, which is class 1, and those circles, which are class number 2. We want to reduce it from a two-dimensional space to a one-dimensional space, assuming for the moment we just have two classes, so that they can be separated very well. In the original space, I say, okay, yeah, I can separate them very well. So if I'm separating the points over here, these are all crosses, these are all circles, I'm happy. But depending how my dimensionality reduction looks like, I may get a different result. So what we can do is we can look to different properties of those points. We can say, okay, we can compute the mean between those points. And it's the mean of the other points. So the mean of the points of class 1 and the mean of the points of class number 2. We can say we can now take any u, so in this case just have drawn it here, but I can choose any of those, and this would be my new dimension. I want to choose now the u in a way that I can separate those classes well. Okay, let's see what happens if we would project the individual means to this U. Okay, this is mean number 1. This would be projected over here as we call it M1. So the mean is in the original high-dimensional space, and the M is the mean in my low-dimensional, one-dimensional space in this example. Same thing happens here. The point is projected over here. And I can also look where are all the other points projected to, and this gives me those lines, those intersecting lines over here, and those intersecting lines over there. So now I can draw 3 quantities in here, or 4. The projection of the mean, the first class, the projection of the mean of the second class, then I can evaluate how much are those classes actually spread out, those data points spread out. But I can now say, okay, these are different quantities for which I want to have different results. So the first thing I want to have those projected means M1 and M2 as far away from each other as possible. The further those are far apart from each other, the easier the classification should be. At the same time, I have to look into the spread. I want to kind of minimize the spread in each class. So the smaller this gets, the closer they go to the projected mean, and the better they should be separated. So maximize the distance between M1 and M2 and minimize S1 and S2. If I find a way to formulate this as an optimization problem, so I want to find the U so that M1 and M2 are as far away from each other and S1 and S2 are as small as possible. Then I found a new dimension which allows me to separate those classes well. Okay, so we want to find a U, so this vector over here, so that M1 minus M2 is large and S1 and S2 are small. So a small spread in each class, a large difference of the means of the classes. And this allows me, then this U is likely to allow me a good spread. Of course, maybe there is no dimensionality reduction which can achieve that. This can happen. But we want to find the one-dimensional space, a linear space, so that this actually holds. This is our goal. That's what we want to achieve. Okay, now we say we want to maximize this one and at the same time minimize those two expressions. So let's investigate, let's understand a little bit better what is M1, what is M2, what is the spread. And then put all of that into one single function and see if we find the minimum of this function. It's kind of the main thing that we are going to do now in the next, 30 minutes or 20 minutes. Okay, so what is M1? We said M1 is the projection of the mean of the first class onto the vector U I'm looking for. So this M1 is a function of U. And then I have this kind of weird expression over here, and this kind of a weird variable C pops up here as well as here. So C is an indicator variable. It simply means if C equals to 1, then I'm class 1. If C is equal to 0, and actually in class 2. So if this is class 1, all those guys here would have a C equal 1 assigned to it, and they would have a C equals 0 assigned to it. So this is kind of the label, the supervised information that is in the system. Okay, so if C equals 1, it means that there is they belong to class number 1, and C equals 0 means they belong to class number 2. So what this expression does here, so if we ignore U, this U for the moment over here, we have the sum over all xt, data points xt, times ct. So this is 1 if you're in class number 1, and 0 if you're in class number 2. So it will simply count will only count those points which are which belong to class number 1. And then what I do is I project those individual points onto my vector U. The same thing I can do over here. I have 1 minus C, so this value gets 0 if I'm in class number 1, because then it would be 1 minus 1. And it stays 1 if I'm in class number 2. So this only takes into account the points of for M2. And I simply divide that, just counting the number of points in class 1 and the number of points in class 2. What I therefore did is I computed the mean for the elements in class 2 and the mean for the elements in class 1 projected onto U. Is it clear how that works? Sorry?
I don't understand the law.
You don't understand this expression? This just counts the number of elements in class 1. So what I do in here, so let's maybe write that slightly differently. So we said before, if you go back to this plot, so this is the projection of the mean 1 onto U. So this is M1 is U transposed and the mean. And then I say, okay, this is U transposed. What is the mean? The mean is the sum over all points xt which belong to class number 1. Right? I'm only interested in those class number 1. So write this as ct. So they are 1 if xt belongs to class number 1, 0 otherwise. If I take this expression, I would simply sum up all the points. And I need to divide by the number of points which belong to this class. And this is simply the number of times this CT has been 1. So this element is here just, this is equal to number of points in class 1. And you can do the same thing for class number 2. Oops. Yeah, I can do the same for class number 2, but instead of C, I use 1 minus C because it's just the opposite event.
I see the left one, that's clear.
Yeah.
But the right one, so the sum of all CTs is the sum of all beta points, whatever, is 1.
It's not this is not a sum. These are just indicator variables. So CT equals 1. CT equals 1 means that, okay, maybe this was too short. Maybe this, so I should have better written here, means XT belongs to class 1. So CT equals 1 means XT belongs to class 1. Can you read that? And CT equals 0 means XT belongs to class 2. And 1 minus CT equals 1 as a result of that means XT belongs to class 2. It's the same thing. If I can either write this should be 0 or this should be 1. It's just the nice thing is it's a very nice way for compactly writing like this without having if statements kind of in this equation.
But to get some algorithm problems because divided by 0, they don't like it that much.
No, therefore, no. So what I do here is I take.
It's just the numbers now.
This is what this gives me. It's just the number of elements in M2.
Okay, yeah, got it.
So unless I am in the situation where there is no point in class 2, then of course I will divide by 0. Otherwise, this gives me the number of points in class 2. Okay, any further question? Okay, so we're done with M. Now let's look into S, to the spread. So we can just look into how scattered those samples are, and we just look into the one-dimensional space over here. And that's something which is actually very, very related to the variance, just only the 1 divided by n minus 1 factor is missing. So this is the spread S1, or a scatter, of the elements in class 1 projected onto my vector u is I'm taking the data point, projecting it on u, subtracting the mean squared. Summing over all elements, taking only those into account which belong to class number 1. So if we ignore the class assignment, we can ignore that. Then it's simply where's the data point in the 1D space minus the mean of the data point in the 1D space squared. Very well known. And then I just do that for only those points which belong to class 1, and I do the same thing only for those points which belong to class number 2. Okay? I could have a normalizing factor in here, and then I would have the variance, but I'm just looking to the spread, so this so-called scatter, then it's just without the 1 divided by n minus 1 factor over here. Everyone happy with those expressions over here? Or is there anything I can clarify regarding those expressions? Anything which needs clarification? So the one thing is just, where will the mean be projected to? This is what this is. And what scatter or what spread will I have away from the mean along the projected dimensions for the class number 1 and the class number 2? Okay, now I can very easily put that into an objective function, so in a function I want to maximize or minimize. So the difference between those two guys should be large, and those two values should be small. So the easiest way to do that is, okay, let's simply say this is m1 minus m2. So this should be large, and divided by s1 plus s2, and this should be small. So if I'm maximizing this expression over here, I'm maximizing the difference between the means, and I'm minimizing the scatter or the spread that I have along this dimension. So this is squared difference of the mean and kind of the in-class scatter. In class 1 and in class 2 simply summed up. So what LDA does is says, okay, this is my objective function. I'm just maximizing this objective function, and I'm selecting the u which maximizes this function. Okay, idea clear? Okay, so whenever there's something not clear, just interrupt me. See, the only thing I'm now doing, I'm kind of rewriting this a little bit so that later on it's a little bit easier to compute, for example, the first derivative of the thing if we want to maximize this function. So we can actually look to the first expression over here, m1 minus m2. m1 minus m2 squared can be written as, so these are the projections of the mean. And it should be clear that they depend on u, therefore I'm rewriting that so that this expression depends on u, because my objective function in u. So this is the mean of the class number 1 projected along u minus the mean of class 2 projected on mean of class 2 projected on u. This should be maximized. Okay, let's actually rewrite that and actually formulate this. This is a squared function as a matrix. Mean 1 minus mean 2 means 1 minus mean 2 transposed. And this is something which I can simply rewrite in that way. It's something called the between scatter matrix. So how far are the means scattered away from each other? And then I can actually write this in this simple form. So u transposed, my matrix S, and u. It's a quadratic form, the same way as this is a quadratic form. It's just kind of rewriting that to make clear that these are actually quantities which depend on u. Now I can do actually the same thing for S1 and S2. Say, okay, S1 squared is the sum of all elements of my original data points projected on u minus m1 and my indicator variable. You can say, okay, this m1 is again nothing else as the mean of the class number 1 projected onto ut. So I can move ut out. So I have ut, x minus the mean, x minus the mean, only computed for those elements which belong to class number 1. So just take the data points, subtract the mean, transposed, and then, again, I have a quadratic form which is called the within scatter matrix, because this is now the scatter within the class. Again, quadratic form, a function which is quadratic in U. And this is important because in the end, I want to solve my objective function with respect to U. So I turn that into quadratic functions with respect to U. What I then want to do is I want to compute the first derivative. So you can do that for S1, I can do that for S2. If I do that for S1 and S2, I can even combine that, saying S1 plus S2 is this expression we had before, plus 1 S2, and even combine this at the total within scatter matrix. It's just combines the matrix S1 and S2. So what I have a quadratic form on top, a quadratic form on the bottom, and the only thing I need to do is I now have my objective function, which I have over here. This is the result over here. I need to compute the first derivative. That's the first derivative to 0, and then solve with respect to U. You can actually do that without going to the details, saying the value that maximizes U is the inverse of this matrix U, the total within scatter matrix, and the differences of the original means, how far they are away from each other. So if I'm finding the optimal dimension that I want to have, my U that I want to have, if the U which maximizes this function is exactly given by this expression. So it takes into account how is the spread of this function which depends on U, which defines the direction, and how far the means are actually away from each other. So this is a matrix, so this is a vector which results in giving me a direction of my matrix U. So this is the difference in the means. This is the inverse of the sum of the scatter matrices, so of this guy over here, which was S1 plus S2. Just compute the inverse, and then I solved this function. I just solved that by computing the first derivative, setting it to 0, and then obtaining this result. So by using that, I obtain a U that allows me, that maximizes this objective function, so my objective function over here, which we define in a way that it allows me to separate my classes S1 and S2 as good as possible. So we have done that here for a simplified form. The simplified form is that we just have two classes and k equals 1. But we can do exactly the same thing what we have done here, just the notation gets slightly more complicated. Exactly the same way in a straightforward fashion, having more classes and reducing, for example, to a 2 or 3-dimensional space as well. So we're not limited to k equals 1. And again, this gives me the optimal split of those data points if the data points follow a normal distribution. Because then I have the scatter, which is aligned with the variance, and I have the means. And if I kind of separate the means and reduce the variance under the assumption that this is a normal distribution, actually gives me the best spread. If the distribution is clearly non-normal, so I have, for example, several clusters for class 1 and class 2 sits in the middle between them, this may not give me a good separation of those points. Then I would need probably a different technique in order to achieve that. So if you now compare again as another example, LDA and PCA, so again, my circles are class number 1, my crosses are class number 2. So this is the spread of the points according to in class number 1. This is spread of the point in class number 2. If I would just take those points into account and compute a PCA, this is the dimensionality that PCA would generate. And then these are the projections of the points along this dimension found by PCA. If I use Fisher's LDA, in this dimension, all the crosses will be projected on this area. All the circles would be projected here along this line. So this is a perfect separation of class number 1 and class number 2. So if you now compare LDA and PCA, we can say that what PCA does, it minimizes the reconstruction error. So I take my point from my original space to the low dimensional space and map it back and try to minimize the difference between them. Even if the difference is small, this small difference can be the key element for the classification. These were the example. So this example shows exactly that. Just as the slight variation where they are in this direction makes the difference for the classification. And therefore, LDA takes a different approach. It says, I don't want to minimize the reconstruction error. What I want to maximize is how well I can actually distinguish my classes, separate my two classes. This requires this additional class information. So if we do dimensionality reduction for classification and we have our labeled training data, LDA is the approach that we should use in order to do dimensionality reduction. If we don't have any supervised information, so if we have an unsupervised problem, then PCA is the standard way to actually tackle the problem. So there's a difference between PCA and LDA clear. So there are two problems which should be applied in different situations. So both assuming that the data can be represented well by the first two central moments of my distribution of points, and only if this is the case they actually provide good results. They work surprisingly well also in other situations, one has to admit, but it's actually, under this assumption, it performs very well. These are both linear techniques, so linear dimensionality reduction techniques. And I want to quickly use the chance to highlight another technique, and just will introduce it very informally, which is called LLE, or locally linear embedding, which is nonlinear dimensionality reduction technique. Just to give you an idea that there are also other techniques to do that and how those techniques may work. And one of the motivating examples of LDA is actually what is also called this Swiss roll over here. So what we have in here, assume this is ours, so we have a three-dimensional world, and the data point that I have follow this what is called a Swiss roll, like the sweet cake, a Swiss roll. And this Swiss roll can actually be represented in a two-dimensional space. One dimension along this line, and one dimension along this line where you see where the color is formed. The only problem is in here is that it's clear that we will not find a linear mapping from our original space to this kind of warped shape so that we can actually represent our points well in a two-dimensional world. So if we would apply PCA, we won't get good results. If we go for another technique, this is actually LLE, it will actually allow us to encode this kind of Swiss roll information in here and map that to a two-dimensional space. So where one dimension is along this illustration here of those white points, and the other one is along this direction. So this is not, so here it may be expressed by a linear function, it's just my vector that I have. Here this dimension has a different shape. So it's kind of the difference clear why we may use a nonlinear technique for this type of problem. Okay, what LLE, sorry, not PCA, what LLE does, it says, okay, I don't want to make any assumptions about how those points are actually scattered. The only thing I want to achieve is that actually a neighborhood information is maintained. So whenever a point is a neighbor in my original space, it should be also a neighbor in my latent space or in my low-dimensional space. Okay? That's kind of one of the key insights in LLE or key ideas of LLE. Maintain neighborhood information. So I want to map from the high-dimensional space to a low-dimensional space by maintaining the neighborhood information. And in this way, coming up with a locally linear embedding. That's where the name comes from. Locally linear embedding. That on a kind of very local scale here, this can be seen as linear, but on a global scale, it's a nonlinear mapping. It basically has three steps. The first step is actually, for every point, find its neighbors in a defined neighborhood. So in a small neighborhood, look for neighboring points. And then compute a weight vector that allows me to reconstruct this point that I have for which I computed the neighbors by a weighted sum of its neighbors. So I have a data point, I select its neighbors, and I say, if I compute a weighted sum from my neighbors, I can actually reconstruct this point. And then the third step is, for this reconstructed point, find these latent coordinates so that the same weight matrix still recovers this point in this lower dimensional space. So in a small animation, how to do that. Let's say we have this space over here. We select a point. We do that for every point. So this is my selected point in orange over here. And I query a certain number of neighbors, or up to a certain distance. And these are the red points over here. So these are my neighbors. First step is just selecting those neighbors. And this, again, can be whatever, a crazy n-dimensional space. So the first thing that we do is we say, okay, what I now want to do is, if I take out this orange point, so I take away this orange point, I want to be able to reconstruct this point just by a weighted sum of its neighbors. So whatever. 1 times this point, plus 0.8 times this point, times 0.1 times this point, and so on. So this gives me a weight for every point, and the dimensionality is the number of neighbors that this point has. So what I do is exactly what the second step does. I compute weights for every pair of points, a weight matrix, saying, okay, this point contributes for reconstructing this points based on these neighbors with a certain factor. And these factors are stored in W. So a lot of elements in W will be 0. There's those points which are far away. But for all neighbors, we have these reconstruction of points. So this step is actually a very simple point. The only thing we say is we have a point, we select its neighbors, and we say, let's try to reconstruct this point by a weighted sum of its neighbors. Neighbor 1 times, whatever, 0.1. Neighbor 2 times 0.3. Neighbor 1 times 0.8. Neighbor 4 times minus 0.1 maybe. We just have a weighted sum of the coordinates of the neighbors to reconstruct this point. We may not fit it perfectly, but we maybe come close. And then the third step is actually going to a low-dimensional space. So these are not called X anymore, but A. And this space is, for example, now not n-dimensional anymore, like this one, or 4-dimensional. It's just 2-dimensional anymore. In the way that we say we want to find the coordinates so that I can still use the same weight matrix that I used here to reconstruct this point in the lower dimensional space. And this weight matrix, what it does, it kind of represents the local neighborhood information. It says how much of this neighbor and how much of this neighbor, how much of this neighbor and this neighbor allows me to reconstruct this coordinate. And this should hold in my original space, and this should hold in my low dimensional space. And these are again then the three steps that I do. First thing is just nearest neighbor query. Nothing else happens. Just identify for every point its neighbors. And what I then do, this may sound a little bit tricky, but it's actually not tricky. I have an error function which depends on my weight matrix W. And I simply say, this is just a sum of all data points, of all neighbors, the original data point minus the sum over the data points times the weights. So this just means how well can I reconstruct the data points based on the reconstruction of its neighbors. Original data point, reconstruction from its neighbors. Just want to find this W so that this is as small as possible. Right? So this is just the error function that I've written, and then I just treat this as a general minimization problem saying find the W so that this error function is minimized. In the perfect case it's 0, then I can perfectly reconstruct the point, but this is something which will in general not happen. So I will have W's which are kind of small. Then the third step is a second minimization problem where I say, okay, now I have my lower dimensional points A, my coordinates, so that I can take the coordinate of this point in this latent or low dimensional space and subtract the reconstruction of exactly the same neighbors, which exactly the same matrix I identified before. And then I perform a second minimization problem, which gives me then the latent coordinates for that original data point. So what I use is I have two error functions I need to minimize. The one was computing the weights through reconstruction of the neighbors, and the next one computing the low dimensional coordinates given the weight matrix. And if I do that, I actually obtain those results, again, the Swiss roll example we had in the beginning, or even other types of environments where I have a clearly nonlinear mapping from, in this case, 3-dimensional space to a 2-dimensional space, where those white things is dimension number 1, and those white lines represent the dimension number 2, which folds into the 3-dimensional space. And all those points here can be expressed by a 2-dimensional coordinate in this example, dimension number 1 and dimension number 2, so that the same neighborhood relation is maintained. This is kind of the trick that I say. I locally reconstruct a point in a linear fashion through its neighbors. And I keep this locally linear relationship, but map it to a different space, but try to maintain it as good as possible. And this is one way how I can do this nonlinear dimensionality reduction. It's actually a quite popular technique which can be used to do that. So it's a nonlinear dimensionality reduction technique. Again, it's an unsupervised approach. I don't need any training data or class labels that I need to do. And the key objective of this approach is to maintain the local neighborhood, do a locally linear reconstruction, and find the low-dimensional coordinates so that this neighborhood relationship is maintained. It does so by solving two minimization problems. One for computing the weights, the second for finding the latent coordinates. And this actually brings me to the end of the lecture today. So the overall topic today was dimensionality reduction, and we looked into 3 different techniques on how to do that. The first one was principal component analysis, which is kind of an unsupervised approach. I don't have any class information. And the goal is to minimize the reconstruction error. Then we looked into an example of PCA using eigenfaces, how we can actually use that, why this is useful. And then we said, okay, if we now tackle classification problems, PCA may not be enough because I'm not necessarily interested in reducing the reconstruction error, but I'm typically interested in being able to separate the classes as good as possible. And that was kind of the objective of the LDA approach. And then finally, I just gave a small outlook on how nonlinear dimensionality reduction could look like, which do a kind of local, they work locally linear but not globally linear, trying to find a mapping for more complex structures. That's it from my side. I hope you enjoyed that. And questions, are there any questions? So if you want to read again about that, PCA is something you find basically everywhere, a good description about PCA. The description of LDA, I again strongly recommend the Alpayadin book. This is the book I personally found very easy. I also used the notation from the book, which I really appreciate for understanding LDA and for actually also looking into the generalization from 1D for k equal 1 to a larger dimension. It's done very nicely in there. First doing everything in 1D, then generalizing that to multiple dimensions. So just as a recommendation, if you want to look through it again, that will be my first resource to look into. That's it from my side. Thank you very much for your attention, and we see each other on Thursday. Thank you very much.